All right, so this is week 1, Monday, October 1, and we got to talk Monte Carlo methods. Okay, so we left off on Friday, and we did like the most basic example, and we said the big picture Monte Carlo methods was that you want to find, properties of a distribution, something like the mean, something like the variance, or anything else that you might have done in 100B or 100A, whatever, wherever you learn probability. And we said in our Monte Carlo class, we're not going to try to tackle these answers analytically. We're not going to try to do integrals or anything like that. We are going to just use randomness on the computer. So we said, let's say you have an exponential distribution and you want to know the mean and variance of the exponential distribution. How do we go about doing that? The Monte Carlo approach was to generate a bunch of values from the exponential distribution and then calculate the mean of those random values, calculate the variance of those random values, right? So, the Monte Carlo approach uses randomness and many trials instead of mathematical analysis. Okay, and this is perfect for someone like me who struggled with math beyond basic calculus. Okay, so beyond basic calculus stuff, like math is hard. So I don't know what this is, but I'd rather avoid doing math. So I think the example was x comes from an exponential distribution. With lambda equal to 3, what is the mean and variance? Okay, and then the true answer from math was the mean is equal to 1 over lambda and the variance is equal to 1 over lambda squared. That's the true answer from math, and you could do what you learned in 100B to get these answers. What we have is for Monte Carlo, is we used the random exponential function. I'm sorry, not just how do I do this? Can I just move this over? So we'll have, maybe like 10 to the 6. We generate a million values from the random exponential distribution, and then we would just ask for mean of x and the variance of x, right? And this will give something close to 1/3 and something close to 1/9, maybe not exactly. Okay, that's the Monte Carlo approach. And so this concept of being able to generate values from a distribution, generate random values from some probability distribution is very, very important to Monte Carlo methods. We need to be able to generate values from a distribution. This was easy because R has the exponential distribution random generator function built in. Okay, that's easy for us. But what if you have a different probability distribution? What do? We need to have a way to generate values from a probability distribution. Okay, so I should say these provide estimates of mean and variance. Okay, so being able to generate random values from a probability distribution is key to Monte Carlo methods. All right, so today we are going to look at one method for generating values from a probability distribution, whatever it may be. Okay, so today we learn the inverse CDF method. Okay, and that's what we'll do. Okay, so all right, so we'll just start off. So the basic idea is let's talk about what a PDF is, what a CDF is, and what an inverse CDF might be, right? So let's think of just the normal distribution. Okay, so the normal distribution has a PDF, which is the probability density function. Okay, and in the normal PDF, if we do the standard normal, we'll say phi of x, this is the standard normal, will be 1 over the square root of 2 pi e to the negative x squared over 2. Okay, anytime you see an e to the negative x squared, it's going to look like a normal distribution. Okay, this other stuff, 1 over square root 2 pi, why do we have a 1 over square root 2 pi in there? Its only purpose, well, is so that it becomes a PDF. All right, what are the rules for a PDF? Can any function be a PDF? No. Okay, in order for a function to be a PDF, there's 2 requirements. What's that? What are they? Yeah?
Area has to be 1.
The total area under the curve has to be 1. And what's the other one? It always has to be positive. Okay? You can't have any negative values in your PDF function. Okay, so there's only 2 rules, right? The area under the curve has to be 1. And no negative values. Okay, and so this 1 over square root 2 pi, that fulfills the purpose of area under the curve equals 1. Okay, you don't put that in there, and then the area under the curve will be square root 2 pi. Okay, so anyway, the PDF of the normal distribution looks something like that. Okay. All right, and what is the CDF? This is the cumulative distribution function. And what's this? This is the integral from negative infinity to x of the density function from, of f of t dt, right? And so if we did the CDF of the normal distribution, we would get the integral from negative infinity to x of phi t dt, okay? And there is actually no closed form solution to this. Okay? This function you can't integrate. But anyway, that's conceptually it's okay. The CDF looks like this. Something like that, right? And this goes from 0 to 1, right? Something right here. So this is our CDF, normal CDF. Okay, so it maps the input. The inputs go from negative infinity to positive infinity, maps the input to the range. What's the range of the CDF? 0, 1. So the inputs go from negative infinity to positive infinity, and then the output, the range, is 0 to 1. Okay. And so the inverse CDF inverse, what will this look like? The inverse of a function is basically a reflection across the axis y equals x, okay? And so the inverse function will look like this. Something like that, okay? So it goes from 0 to 1. So the inverse, so now the input domain is 0 to 1, and the output range is negative infinity to positive infinity. Okay. So we have the density, the CDF, and the inverse CDF. Okay. And this is just for the normal distribution. All right. All of these functions have exist. They're already pre-programmed in R. Okay. What function do we use to get the density function in R for the normal distribution? This is in R. You use d norm. Okay, d norm will give you the density function. So d norm of 0, what is d norm of 0? Well, I don't expect you guys to know this off the top of your head. It's 1 over square root 2 pi, okay? because you just plug in 0 here, right? E to the 0 becomes 1. D norm of 0 is going to be 1 over root 2 pi. Let's see if I can get this. I'm going to have to get like a wireless keyboard or something. All right, so if I type in D norm, yeah, okay, 0. All right, let's see. All right, that's 0.398, which is the same as 1 divided by square root 2 times pi. Okay? D norm 0. All right. No big deal. Okay. What is the function in R that will give us the... Is something happening here? Okay. The CDF. In R, to get the CDF, what is the function we use? The normal cumulative density function. You guys are breaking my heart here. P norm? Yes? Okay, so what will P norm of 0 be? So, sorry, I should go back and I should say D norm of 0 is going to be 1 divided by root 2 pi, which is about 0.39, what? 399. Okay. P norm of 0, what will that be? What's that? 0.5, right? So you go to 0 in, and this is going to be at 0.5. So P norm of 0 exactly is 0.5. This is equivalent to, you know, in the back of your intro stats textbook, so you have the cumulative normal table, okay? You type in P norm 0, you get 0.5. What would happen if you type in P norm 1.96? .975, right? Because when you go up to 1.96 and down to negative 1.96, you have 95% in the middle, okay? So indeed, if I type in P norm 1.96, I get 0.975 or something very close to it. P norm of 0 gives me 0.5 exactly, all right? Okay, and then lastly, for the inverse CDF, what do we have in R? So we have D norm, we have P norm, and we have Q norm, right? So the inverse CDF is Q norm, okay? And this pattern of D, P, and Q apply to all the built-in distribution functions in R. D will give you the density, P will give you the cumulative distribution function, the CDF, and Q will give you the inverse CDF, okay? So what would Q norm of 0 give me? Q norm of 0 would give me negative infinity, right? Because we're asking what is the value that will correspond to a CDF of 0, okay? Negative infinity, right? Q norm of 0.5 will give me 0, and Q norm of 0.975 will give me 1.96, because it's asking what value will give me this CDF. And so indeed, if I type in Q norm of 0, okay, it tells me negative infinity. If I say Q norm of 0.5, okay, I get 0, and then Q norm of 0.975, I get 1.96, right? And then if you give Q norm anything outside of the range of 0, 0 and 1, like if I did Q norm 2, okay, it tells you you're not going to get a number, all right? There's nothing that's going to give you a 2. Okay, so that's how it goes, all right? So what we can do is we're going to make an assumption that we are able to generate values on the range 0 to 1 at random, okay? So we're going to, this used to be a problem, but now we just say, it works now, okay? So assumption is we can generate values U from the uniform 0 to 1, okay? So this will just mean we can generate values, random values, drawn from the uniform distribution on the interval 0 to 1. This used to be a complex thing. You can look up the history of pseudo-random number generators, okay? PRNG. Pseudo-random number generators. All right. But we now have, high quality random number generators that that pass like a barrage of tests, right? Because it's hard to prove that something is truly random, and actually pseudo-random number generators by definition are not random, okay? Because a computer is supposed to behave in a predictable manner, and so it's generating values, and they are inherently not random, but they behave like random numbers, okay? So I mean philosophically, is anything in life truly random? And this is hard. Maybe at the quantum level things are random, but maybe that's just because we don't have a full understanding of what's happening at the quantum level. Maybe they are not random, or maybe they are. I don't know, But like if I flip a coin, it feels like it's random, 50-50 chance of getting heads or tails. But if you knew the exact strength of my thumb and the velocity at which the coin took off and its rotational and angular speed and all of that, and how likely it is to bounce on a table, I don't know. You might be able to predict with 100% accuracy if you had all of those unknown variables, like how the coin will land. But anyway, we're going to just say we can get random numbers, all right? Our computer uses the Mersenne twister, okay, or Mersenne. And I tried to read the paper on how the Mersenne twister works, and I didn't understand it. It was too complicated, okay? It talks about, I don't know, bit shifting and all of this, and basically the conclusion I came to was it's a good random number generator, okay? And it was so good. Like before this, they had things called linear congruential number, I don't know, different things that like were easier to understand. I read those things and I was like, okay, that kind of makes sense. And then somebody came along with the Mersenne twister, and everybody loved it. And within a few years, like it became the random number generator for R and MATLAB and a bunch of and Python and stuff. And it's like it's a good one. Okay, I don't know how it works. But anyway, now that after the Mersenne twister came along, people stopped trying to bother improving random number generators, okay? We're just like, oh yeah, this one's good. So anyway, some work still goes on in random number generation, but not really, okay? So anyway, we're going to say we can generate values from random uniform 0, 1, okay? In R, to do this, how do we generate random values from 0 to 1? What is the function we use? RUnif, exactly. So we use RUnif n, okay? We just say how many numbers you want, and it will generate random values from 0 to 1, okay? You can put in other values, like there's optional arguments for the minimum and maximum, so you can have it generate random uniform from 0 to 100 or 5 to 7 or something like that. But in general, random uniform will give you a random value between 0 and 1. Okay, that's great. So if we have u coming from random uniform, then, and if we have the inverse CDF, we can get random values from the desired distribution, okay? So to generate random values from the normal distribution, you know, what we do is we would generate u from the uniform distribution, and then plug in to the inverse CDF. Okay, so you have so this is the inverse normal CDF. Okay, and so maybe you get a random value right here. This is your u, and you come along and you plug it in here and you get this value, and this is going to be your random z. Okay, so plug in u to f inverse, and that's it. Okay, so you just say z is equal to f inverse of u. And now you have z will follow, z will be is a value drawn from the normal distribution. So conceptually, it's very simple. All you do is you have the CDF, you invert it, and if you generate random values from 0 to 1, if you plug them into the inverse CDF, you're going to get random values according to the density function that you want, according to the probability density function. And this is actually how R works. When you ask R to do random normal values, it just generates random u's, plugs them into the inverse normal CDF function, and gives you random normal values. Okay, so let me just kind of show you this. So let me, all right. So let me just say x. Here, let's do set seed. Is this working? Okay, so we're going to do set seed. All right, let's just set seed 1. Okay, and then I'm going to say x is random uniform, let's ask for 10 random uniforms. Okay, and let's print out x. Okay, these are the random uniform values. Now, for whatever reason, R only uses every other value, okay? All right, so let me just also go back to set seed 1. And then let me ask for 5. Whoops. I will just say R norm. I'm going to just ask for 5 random uniform numbers. Okay? So I ask for 5 random uniform numbers, and there they go. And I just want to show you that if I type in Q norm, so this is the InverseCDF function, and can I highlight this? Control copy. All right, let's come over here and let's paste this number in here. Okay, if I take that random uniform value that I generated using our UNIF and I plug it into the inverse normal CDF function, I get the value that our norm generated. Okay, and if I take the next value, and again, for whatever reason, R only uses the odd numbered things, and if I say, okay, let's do Q norm of this value, okay, I get the next value, 0.1836433, and you can see, so you can trace back how is R generating these random normal values. When you ask for R norm, what R is doing is it's generating R UNIF and it's plugging them into Q norm. It's using the inverse CDF method. It's saying, let's generate some random uniform values. Let's plug them into the inverse CDF function, and whatever this spits out will be our random normal value. Does that make sense? How this is working? Okay, and indeed, if I come along and I say, all right, let's just make sure this is working, a histogram of R UNIF, let's ask for a bunch of these things. Okay, so there's a million random uniform values, okay? And if I ask for a histogram of a million R normal values, random normal values, 10 to the 6th, okay? So I'm just, indeed we get the normal distribution. So when we use these methods to generate random values, we indeed get values that follow the desired distribution, okay? And so our norm, when we ask R to generate random normal values, it's just taking our UNIF, okay? This is what X is up here, and it's plugging them into the inverse CDF function, and it's reporting those values back. So 0.6264538 is just this number in the inverse CDF. And this number here is just this third number here. And then if I took this number and I plug that into inverse CDF, that would produce this negative 0.8356. Okay. I don't know. Is that kind of neat to see, or not really? I always like figuring out how things are working on the computer. So I was excited. Maybe you guys are not as excited, but it was exciting to me. Okay. So this is just an illustration of this concept of the inverse CDF function, right? And so okay, so this is, I guess, based on their, I guess maybe I'll throw this theorem in there, which is the foundation for how this works. Okay, so this is the probability integral transformation. Okay, so if X as a random variable with CDF equal to capital F of X, then F of X comes from the uniform distribution there, all right? So basically it's just saying if we draw a random value X, then F of X will follow distribution. Okay. And so mathematically, this is what the inverse CDF looks like. The inverse CDF method is basically U comes from the uniform distribution, and then you plug U into the this, and the inverse CDF is going to be defined as the minimum value of t such that f of t is greater than or equal to u. Okay. That's a 0. Okay. And then this whole minimum stuff, the minimum is just there so that it works for discrete distributions, okay? I think today we will soon run out of time. Let me just do something for like the exponential distribution, and then we'll call it. All right, so we'll do maybe like a worked example. Okay, so first we're going to say the PDF of the exponential f of x is equal to lambda e to the negative lambda x, and this is for x greater than or equal to 0, right? All right, and so the CDF of the exponential capital F of x is going to be equal to the integral from 0 to x of lambda e to the negative lambda t dt, okay? And so when you do this and you solve for this, you're going to get 1 minus e to the negative lambda x. Okay, so that's the CDF. So this is, all right, so now we're going to find the inverse CDF. Okay, so what we'll do is we'll set f of x equal to u, and then solve for x. Okay, so I've got 1 minus e to the negative lambda x equal to u. And then I just move some terms around. I got 1 minus u is equal to e to the negative lambda x. I'll take the log of both sides. This being the natural log. Wait, did I mess something up here? Alright, so so what we can do is we can say, all right, and then at this point we can say if u comes from the uniform 0 to 1, then 1 minus u also comes from uniform 0 to 1, right? So we can kind of simplify this to just be log of u, where okay. So we can do that. All right, and then so this is how, if we wanted to make our own function to generate random values from the exponential distribution, we would draw u from the uniform and then plug them into our inverse CDF function. And this will produce values according to the inverse, according to the exponential distribution. Okay, we'll stop here for today. We'll pick up on Wednesday. We'll look at the discrete case, and we'll see you guys then.